full work. First is about the video supervisation, and the second is unsupervised segmentation.
And for the outline of the dissertation is introduction, literature review, video super resolution, and talk about the unsuper segmentation, experiment result, and conclusion. And for the first part, we will talk about the introduction. So here the super resolution image is useful for improving image quality and restoring lost information from the image. And for image super resolution is very challenging, and the smaller the input, and it will be more difficult to complete. And for video super resolution, it's different with the single image super resolution because it's a relation between the frame as the temporal feature. And here we use the firewalk dataset because in the firewalk they have the unique characteristic, especially for the video super resolution that have a motion feature. It can show clear motion by the fire trajectories in the firewalk. And also this firewalk doesn't have the our dataset doesn't have the segmentation label, so it's need to do the manual labeling. And for the firewalk, this task is uh, hard to do, and for that we have the unsupervised approach to solve the problem. And our objective research is first to establish a novel super resolution method using video input and using the generative adversarial network. And the second is develop the unsupervised segmentation model to segment multiple objects in the video. And the last is investigate the short-term and long-term consistency between frame to enhance the performance in the video super resolution. And the scope of this study is the first work focus on the create higher resolution image for each frame on the video and keep the quality consistency between the frame. And for the second work, it's work on unsupervised approach due to the lack of the ground truth for the dataset firewall. And next is talk about the literature review. This is the we use for the basic knowledge for our research. It's talk about the super resolution, the GN, the optical flow, and the image segmentation. For the super resolution, there are two kind of super resolution: the single image and video super resolution. Basically, the video super resolution is similar to single image super resolution, but in the video super resolution, we need to see the temporal information. While if we directly use the multiple image and separately doing the super resolution, it's missing the temporal feature between the frame. And for the generative adversarial network, it's widely used in the image related tasks like image to image translation and image generation tasks. And image generation, they create the new image from the random noise, and for the image to image translation, they translate one image to another image with different style or color. And in spite that approach for the image to image translation, we assume that GN also should be work for the super resolution, because we think that the super resolution is like to change the low quality of image into the high quality of image. And next is for the optical flow. Here, for the temporal information in the video super resolution, we use the optical flow that have the movement of the image. So we use it for the temporal information. And for the image segmentation, the aim of the segmentation is to achieve the pixel classification in the image. So in the supervised, they need to segment the image similar with the ground truth data, while in the unsupervised, the data is have no ground truth, so it's do it no supervision. Like in our case, we use the unsupervised because the lack of the ground truth data for training. And next, we will talk about the video super resolution in detail for our first work. So in video super resolution, we propose the multi-hub video super resolution with long-term consistency, and it's using the GN as the uh, basic network because it's proven in the several image processing tasks, and it should be also good for the super resolution. And here the video super resolution have the temporal information that need to uh, highlight for the sequence of the frame. And many VSR method use the motion estimation to maintain the motion continuity of the video. And another method propose to use the multiple frame as the input. And most of the super resolution method use direct scaling from the low resolution into the high resolution target. And for example, if the uh, low resolution is 100 and 100 pixel and the target is 400, they directly uh, do the scaling for from 100 to 400. And we think that if we do the gradual scaling, it can help the model to learn the high resolution. So here we propose the multi-hop video super resolution using the GN, and also we propose a novel long-term loss alongside with short-term loss function to maintain both of the detail of the image and also smoothness of the motion. So the basic idea of super resolution is in, we can see in this figure. So the first, we have the low resolution and we want to create a high resolution image. In our approach, we will do, first we will resize the low resolution image into the uh, bigger size, but still have the low quality, and we want to make this low quality image into the high quality and high resolution. And this task is maybe similar with the image to image translation, and the result will be similar to the super resolution. And so that the contribution of this first work is to propose the multiple times of scaling method called MVSRGN, and also we propose a novel long-term loss for videos per resolution. And here is our proposed method architecture. So we have the multiple hub of GN, and here for the first input is the low resolution input, and we use it to the input for the generator to generate the intermediate output that here it's have two times larger image. And then for the intermediate input will be used for the second GN and produce another larger output. Uh, and this multi-hub will finish until we achieve the target image. And here our purpose is perform super resolution gradually, so we assume that it will make the work easier. The, the assumption is based on this preliminary experiment. So if we do the uh, first step is 2 times scaling uh, compared to the if we directly scaling to the most larger target image, we can see in the PSNR to see the like the distance of the image. So the smaller the distance, so it's easier to reproduce the image because it's have less missing information. So using this idea, we propose our system. And so in our input, we use multiple frame as input, and the main RGB input is the current frame, while the previous and the next frame is work to get the optical flow information and use it together to as the input. And for the generator, the generator is used the unit architecture, and because our method have the multiple GN, so we also have the multiple generator, and each of generator will produce the output 2 times larger of the input. And here, first we before the unit we do the upsampling layer, so the input layer will have the similar size as the output, and then the unit uh, will work to reconstruct the image quality. So we will have the larger image with the better also the better quality. For discriminator, in this discriminator, we just use the discriminator for patch GN, and we didn't do any modification except the input size. In the original, the input size is the same between the width and height, so the output will n by n dimension, while in our input is different in height and width, so it will create m by n dimension. And for the loss function here, we have the short-term loss. It's the spatial quality of the PSR determined by the quality of the super resolution. So here we use the triple loss function. The first short-term loss is consist the adversarial loss, perceptual loss, and MSU loss. And all of this loss is commonly used in the GN for the adversarial loss and another loss, also for the super resolution. And our long-term loss is maintaining the temporal quality is important for VSR, and we propose the long-term loss to handle the temporal problem. And our proposed long-term loss is use the long-term MSE and long-term optical flow. So we have the movement for its frame by frame over time, also the detail from frame by frame over time. And here our short-term loss is using the similar with the previous work, also use this similar approach for the loss function, and we just add all the three loss function to the total short-term loss function that we use. And for the long-term loss, we use the summation of all the MSE loss for the frame, all the frame in one video, in the same video in the sequence. And also we use the optical flow as the another loss to compare between uh, the ground truth and the predicted image or generated image from the uh, current frame and previous frame. And we will add these two loss into the total of the long-term loss. And for the data preparation, we use the several data. First is the Vimeo 90K, and the second is Fit for dataset. These two dataset is commonly used in the video super resolution tasks in many works, and we also create our own firework datasets, which will show the motion more clearly. And for the firework dataset, we do the data collection, data preprocessing, and the data augmentation. In data augmentation, we collect several video and cut into several clips with 10 to 20 frames length. In it's different on the firework appearance in the video. And for the data processing, uh, we after we cut the frames, we also do the resize of the uh, image from the frame. Uh, we make it similar with our model input. And for the data augmentation, we do the random cropping with a 10% padding. And first we crop the image. After we get the crop image, we resize back to the original input image. And next, for the unsupervised segmentation, so the unsupervised segmentation is divide the image into the several segment object, and the target of the segmentation usually is have the similar shape or colors. However, in some cases, it's not effective. Like maybe in the some cases like the firework, the shape and the color is dynamic, and the firework also sometimes has the explosion, and it's affect the brightness of the image, and it will have different result with the clear uh, firework. And so here we use the unit to solve the uh, segmentation by fuse low level and high level image feature, and combining low resolution and high resolution feature through the skip script. And here is our proposed method. It consists of two streams. First is the current frame, and the second is the next frame. And after the unit, we connect it with the two convolutional layer. And the first convolutional layer is work to reconstruct the image into the similar image like the input, and the second is doing the segmentation. And here we use the several loss function. There is a reconstruction loss, correlation loss, and uh, the initial loss. Actually, the reconstruction and the initial is using the same, but the initial is we use the for the segmentation, we use the initial loss using the Cummins clustering as the target. And then after that, we just use the reconstruction and the correlation loss for the image, for the sequence. And as the input, we use the video, and we use each two frame as the input, and we also normalize the value from 0 to 255 into -1 to 1. And for the loss function, for the reconstruction, is just comparing the image and image. And for the correlation loss, its correlation between x and y. X and y is the current frame and previous frame, and it's have the f, b, and s. The f is cosine similarity between the reconstructed image And then the S is for the segmentation result. It's also use the question similarity. Here the B is the hyperparameter that we set to make the F and S equal. So if we have the F is big, so we also want to have the S have the big number. So using this formula, we can make it equal. And next chapter tell about the result and discussion. And the result is and discussion is content of the two. For first is for the video super resolution, and the second is for the unsupervised segmentation. And for this video super resolution, we have several experiments. First is experiment to choose what is the best configuration for the generator. The second one is to show the multi-hop our multi-hop model advantage, and the next is for uh, the learning rate experiment during the training time. And we also do the experiment for all the dataset that we use, like Vimeo dataset, Fit4 dataset, and our Firework dataset. For the implementation detail, here we use the machine with the GPU RTX 3090, and we'll learn using the learning rate 5 multiplied by 10 power minus 4 for the first 70 K iteration, and after next iteration it's decreased by the decay. And for the evaluation metrics, we use PSNR, SSIM, and also we provide the time performance for our model, and also we check the motion evaluation. And for the experiment of the generator, here we have several image input size, and here we try to get the best configuration for input size, because it's affect the unit model, because if we have the lowest ratio between the width and the height, and our unit will be deeper. And here we do in our experiment, we can see that the deeper model have the better result. And also for the experiment on the multi-hop model, here we can see that our multi-hop is better than a single hop with the similar approach in our model. For the in here we also try to remove some of the long-term loss that we propose to know the effect of the long-term loss in our model. And the best result is obtained using our multi-hop with the both of the long-term loss, and we use it for the basic of our model to do the experiment. And here we can see that between the multi-hop video super resolution and multi-hop single image super resolution, in the image we can see that in the left side image is the result of the video super resolution using our approach, and the right is the single super resolution with our also the similar approach. But here if we use the video super resolution, we can see that the detail of image it can create the clear more clear line trajectories compared to the single image. In here it's missing the line trajectories, so it should be have the motion from this point to this point, so it will create a line trajectory. And also in the experiment on learning rate during the training, we do some decrease in the training, because if we continue use the same learning rate, it will stuck in some value. So we need to go back to the previous iteration and change the learning rate and continue with the new learning rate. And next, for experiment on Vimeo dataset, here we compare our result using the MVSR-GN with the state-of-the-art VSR method with the similar dataset from using Vimeo dataset. And here we have the better performance compared to the other, but for the model complexity, it's not the best, but it can compare with the similar complexity model. It still have the better result. And also for the fit for dataset, and here we get the better performance compared to the other. And also in here we improve have the a significant improvement from the another method, because in this dataset it have the longer sequence of image, and our long-term loss it can work well in the longer sequence. And we also provide the detail of the super resolution result between some method that we can find the result. And next, we also check the motion evaluation of our method and another method. Here in the average, our result is better, but in the some of the categories of the video is not as the best, because like in the foliage, mostly in this foliage video, it have a static object, and the movement is have the occlusion with the static object. So, and another is if there is no occlusion in the movement object, we get the higher result. And for the viral dataset, we compare with some methods like TICO, GN, and FR, VSR, also SOF VSR. And here, TICO, GN, and FR, VSR actually it's a similar method, but in the TICO, GN they have the difference is they have the new loss function for the temporal loss function. And here for the firewall dataset, our result is better than the another method that we compared. Yeah, this is the example of our output or our result compared to another. And it's too fast. Yeah, this is the also the video result. And next is the result and discussion for the unsupervised segmentation works. And for this work, we use the learning rate 5 and 4 for 10 powered by -4, and we use the same machine RTX 3090. And for the evaluation metric, we use the intersection of union. And here, because we doesn't have the ground truth, we create the ground truth manually by coloring a different object in different color, and we like separately count each object with our result with have the bigger portion of the label object. And and then the next is the experiment result from our data set. We compare to the common method like Cummins and DB-scan clustering to do the segmentation. And here is the segmentation image result. In the DB-scan and Cummins, they have some problem with the explosion, like we discussed before, because the fireworks sometimes have the explosion in the image, so it have the brighter color, and in the DB-scan and Cummins, it's considered as the different segments. And in our case, the we can solve this problem using our the correlation loss that use the cosine similarities, and the result is we can remove some unnecessary part here, but also it's remove the detail of the part of the firework. And the conclusion is we introduced the new deep learning based framework for video super resolution that include the multiple scaling process, and this multiple scaling help to model to learn gradually to perform the super resolution. And we also propose the long-term loss that effective in terms of contrasting the detail of and maintain the motion of the video. And for the firewalk unsupervised segmentation, it's very challenging to the firewalk is uh, consists of many small detail, and as the dynamic shape and firewalk is not the solid object, and here our segmentation result achieve the better result compared to traditional clustering methods as Cummins and DB-scan. And for future work in our VSR method, the problem is we need to find the best input size of the image, because if we stretch the image too much, like if the different height and width, so the result is different. So we need to find the way how to solve if we have the different size of input and still can generate a good super resolution result. And for the segmentation, we find that using our approach, we can segmentate the firewalk. However, some firewalk objects are still have the wrong cluster, and also it also missing some detail, like it's remove some detail of the firewalk. So we need to find another way to still maintain the detail part of the firewalk, also improve the performance. And thank you for your attention.
So I listened to your presentation. That's a good question.